Out in the deep, quiet corridors of space, something has just broken the calm. Astronomers watching 3I/ATLAS, that rare interstellar traveller from beyond our solar system, have detected a sudden and violent shift. Once gliding smoothly through the void, it now trembles with strange bursts of energy, as if reacting to something unseen. The data doesn't lie. Signals have spiked, light curves twisted, and for the first time, scientists are whispering words like instability and chaos. What could cause an object from another star system to behave this way? Is this just a cosmic coincidence, or the first sign of something larger unfolding out there? If you clicked on this video, you found the right place, because tonight, we're not just looking at what happened, we're exploring why the universe itself might be trembling with it. And before we step deeper into this unfolding mystery, let me pause for just a moment. I am the Sleepy Professor, your companion through these quiet journeys, a place where we explore the universe slowly, carefully, and always with wonder. Chapter 1. The Night We Noticed a Stranger. Picture this. It's past midnight at a quiet observatory, where the only sounds are the gentle hum of cooling fans and the soft whir of telescope drives tracking across the star-filled sky. The world sleeps, but a handful of dedicated astronomers keep watch, their eyes trained not on the familiar constellations but on the spaces between them, searching for something that doesn't belong. Tonight is different. Tonight, buried in thousands of digital images, a computer algorithm flags something unusual, a faint point of light that wasn't there yesterday, moving too fast and in the wrong direction to be just another asteroid. This tiny dot carries with it a secret that will soon unfold into one of the most fascinating stories our solar system has ever witnessed. Welcome to the tale of 3I Atlas, the third known interstellar visitor to grace our cosmic neighbourhood. But before you imagine scenes of chaos or cosmic catastrophe, let me paint you a different picture. When astronomers use the word insane to describe celestial events, they're not talking about panic or destruction. They're describing something far more beautiful, the universe revealing its capacity to surprise us, to show us phenomena so unexpected and wonderful that our carefully crafted theories suddenly seem small in comparison. Our story begins with wonder, not worry. It starts with the quiet excitement that ripples through the astronomical community when something genuinely new appears in our telescopes, something that challenges our understanding and invites us to learn. The insane behaviour we'll explore together isn't a threat to be feared, but a mystery to be savoured, one gentle revelation at a time. Imagine, if you will, standing in your backyard on a clear night. The stars above you have been shining in their patterns for millennia, a familiar tapestry of light that has guided travellers and inspired dreamers since the dawn of human consciousness. But tonight, invisible to your naked eye, a stranger passes through, not bound by the gravitational embrace of our sun like the planets and asteroids we know so well. This visitor follows a path that began in the vast spaces between the stars, a journey that started long before our solar system was even a possibility. This is what interstellar truly means. Not the dramatic science fiction of faster-than-light travel, but something perhaps even more remarkable, a small world, born around an alien sun, cast adrift through the galaxy to eventually find its way to us. It carries within it the chemistry of its distant birthplace, the scars of countless millennia in the cold void, and now, in its brief encounter with our sun's warmth, it begins to tell us its story. The beauty of such moments lies not in their violence, but in their rarity. Consider that in all of human history, we have definitively identified only 2 previous interstellar visitors. These cosmic wanderers are so uncommon that each one becomes a treasure, a message in a bottle thrown across the galaxy, carrying news from worlds we may never see. Our third visitor, 3I/ATLAS, would prove to be the most dramatically expressive of them all, but its drama unfolds not like an explosion, but like a flower blooming in fast forward, beautiful, complex, and filled with subtle details that reveal themselves only to patient observation. As our story progresses, we'll discover how this small world began to change and brighten in ways that no one expected, creating what astronomers lovingly call an outburst, not a destructive eruption, but a spectacular display of cosmic artistry. The changes we'll explore together happen on timescales that feel urgent to astronomers, but remain gentle to the cosmos itself, when 3I/ATLAS suddenly brightened by thousands of times. It did so over the course of days and weeks, fast enough to catch our attention, slow enough for us to study and understand. When it began to spin and tumble in new ways, it did so with the grace of a dancer, not the chaos of destruction. Tonight, as we settle in together, let your mind wander to those quiet observers who first noticed our cosmic guest. Picture them hunched over computer screens, comparing images taken hours apart, slowly realizing that they've spotted something extraordinary. Feel the gentle excitement that builds as the news spreads through the global network of astronomers, each one eager to turn their telescopes toward this new point of light. With our eyes now adjusted to the darkness and our curiosity awakened, we're ready to embark on this journey together. We'll learn how astronomers distinguish between the familiar residents of our solar system and true interstellar visitors. We'll discover the subtle signs that mark a world as foreign, the delicate dance of mathematics and observation that reveals a visitor's true nature. Chapter 2. What 3I means. Names, first clues, and the interstellar signature. Let's drift now into the gentle art of cosmic naming, where each designation tells a story of discovery and wonder. When astronomers first spotted our needle-shaped visitor in 2017, they called it 1I Umoa, the very first object to receive the special I designation, standing for interstellar. The 1 simply meant it was the first of its kind, while Oumuamua, chosen by its Hawaiian discoverers, means scout or messenger from the distant past. 2 years later came 2I Borisov, a more traditionally comet-like visitor that painted a beautiful tale across our skies as it rounded the sun. Now, in our gentle thought experiment, we imagine 3I Atlas, the third member of this exclusive family, detected by the Atlas survey system with characteristics all its own. But how do astronomers know in those first precious hours of observation that they're looking at something truly special? The answer lies in the mathematics of motion, written in the subtle language of orbital mechanics that governs every moving thing in space. Picture a cosmic speed limit, if you will. Every asteroid, every comet, every grain of dust that belongs to our solar system must obey certain rules of motion. They can swing close to the sun or venture far into the outer darkness, but their velocities are forever constrained by our star's gravitational embrace. This creates what astronomers call a velocity at infinity of 0, meaning that even the fastest solar system objects would eventually slow to a stop if they could somehow escape the sun's influence entirely. Interstellar visitors break this rule with elegant simplicity. They arrive carrying what we call hyperbolic excess velocity, extra speed that speaks of their foreign origin. When 3I Atlas first appeared in those Atlas images, careful measurements revealed it was moving just a little too fast, following a path just slightly too curved to be one of our own. Think of it like watching cars on a highway. Most vehicles follow the flow of traffic, bound by the road's curves and the posted speed limits, but occasionally, you might spot a car that seems to be following different rules, perhaps taking an exit that doesn't appear on your map, or maintaining a speed that doesn't quite match the surrounding traffic. That car might be coming from a different highway entirely, following a path that began somewhere beyond your local road system. The orbital mathematics reveals these cosmic highways with beautiful precision. Our solar system visitors trace ellipses around the sun, closed loops that might be nearly circular like Earth's orbit, or highly elongated like some comets, but always ellipses nonetheless. Interstellar visitors, however, follow hyperbolas, open curves that approach the sun from the infinite darkness, swing around our star in a graceful arc, and then head back out toward infinity, never to return. The number that captures this difference is called eccentricity. Solar system objects have eccentricities less than 1, describing their closed elliptical orbits, but interstellar visitors possess eccentricities greater than 1, a mathematical signature as clear and distinctive as a fingerprint, marking them as citizens of the galaxy rather than subjects of our sun. In those first nights of observation, as 3i Atlas moved across the star field, each new measurement refined our understanding of its path. The early data points might seem scattered, uncertain, like trying to trace the arc of a thrown ball when you've only glimpsed it for a few moments. But with each passing hour, each new position measurement, the picture becomes clearer. Imagine astronomers around the world contributing pieces to a cosmic puzzle. One telescope in Arizona captures the visitor's position at midnight. Another in Chile records its location 6 hours later. A third instrument, perhaps in space, adds its own precise measurement. Slowly, these individual points of light begin to trace the unmistakable curve of a hyperbolic trajectory. But 3i Atlas would prove to be more than just another interstellar visitor following a predictable path. Even in these early observations, subtle hints suggested something unusual was about to unfold. The brightness measurements showed tiny variations that didn't quite fit the expected pattern. The astrometric positions, those precise measurements of location against the background stars, carried small residuals, tiny deviations that whispered of forces beyond simple gravity at work. These early clues were gentle, almost hesitant, like the first few notes of a symphony that hint at the magnificent complexity to come. The orbital solution was clearly hyperbolic, clearly interstellar, but it carried with it small uncertainties that suggested this visitor might have its own surprises in store. As we prepare to meet the patient observers who would first capture these subtle signals, let your mind rest in the quiet satisfaction of cosmic detective work. Picture the careful measurements, the gentle accumulation of data points, the slow revelation of a trajectory that began in the depths of interstellar space, and would soon intersect with one of the most dramatic periods in our sun's recent history. Chapter 3. Atlas and the Night Watchers in the high desert of Hawaii and Chile. Where the air is thin and the nights are crystal clear, a network of modest telescopes keeps constant vigil over our skies. These are not the giants of astronomy, not the massive mirrors that peer deep into the cosmic past, or hunt for distant galaxies. Instead, they are the faithful sentinels of Atlas, the asteroid terrestrial impact last alert system, designed with a mission both practical and profound. Picture these telescopes as they work through the night. Each one is relatively small by modern standards, with mirrors just over half a meter across. About the size you might find at a well-equipped amateur observatory. But what they lack in individual power, they make up for in dedication and scope. Every clear night, like a cosmic flipbook, the system takes multiple images of the same regions of sky, typically separated by hours or days. Most of the time, these images look nearly identical. The same stars in the same positions, the same familiar patterns that have graced our skies for millennia. But occasionally, something changes. A new point of light appears where none existed before, or a familiar star-like object shifts its position against the background of more distant suns. Spectroscopes are brought to bear, breaking down the visitor's faint light into its component wavelengths to reveal clues about its composition and physical state. In this collaborative dance of discovery, 3-Eye Atlas would soon reveal itself to be something truly special. But in those first nights, it remained simply a moving point of light, carefully tracked and measured by the patient watchers, who had learned to read the subtle language of celestial motion. Chapter 4. From Pinprick to Path. Building the orbit, imagine trying to trace the path of a shooting star from just 3 glimpses. Seeing it appear briefly over the eastern horizon, catch a second glimpse straight overhead, and then spot it one final time as it fades toward the western sky. From these fleeting observations, could you determine not just where it's going, but where it came from, how fast it's traveling, and when it might return? This is the elegant challenge that astronomers face every time they discover a new moving object in the night sky. Those first few detections of 3-Eye Atlas were nothing more than positions, precise measurements of where the object appeared against the background stars at specific moments in time. But hidden within this sparse collection of data points lay the complete story of the visitor's cosmic journey. The mathematics that transforms these scattered observations into a complete orbital solution is both beautiful and ancient, rooted in the same principles that Johannes Kepler used to describe planetary motion 4 centuries ago. Yet, when applied to modern observations with their exquisite precision, these equations reveal details that would have seemed magical to earlier generations of astronomers. Picture those first few nights of observation. Each time 3-Eye Atlas appears in a telescope's field of view, careful measurements determine its exact position among the stars. These measurements, called astrometry, are precise to a tiny fraction of an arcsecond. Imagine dividing the apparent width of the Moon into nearly 4,000 pieces, then measuring positions to within a single piece. This extraordinary precision is what allows astronomers to detect the subtle signatures that distinguish interstellar visitors from solar system natives. But precision alone isn't enough. The real magic happens when these individual position measurements are combined with the fundamental laws of celestial mechanics. Sir Isaac Newton's elegant equations describe how objects move under the influence of gravity, and they apply just as faithfully to interstellar visitors as they do to the planets in our solar system. The difference lies not in the physics, but in the initial conditions, the speed and direction that an object carries when it first enters the sun's gravitational influence. In those early days of observation, the orbital solution for 3-Eye Atlas remained somewhat uncertain. Picture it as a fuzzy cloud of possibilities, rather than a single, precisely defined path. Each new observation helps to collapse this cloud of uncertainty, narrowing down the range of possible orbits until one clear trajectory emerges from the mathematical fog. The process resembles solving a cosmic puzzle with physics as your guide. The sun's gravity acts as a known force, bending the visitor's path in predictable ways. But the object's original velocity, its speed and direction when it first approached from interstellar space, must be deduced from the observations themselves. It's a delicate balance of measurement and calculation, requiring both precise observations and sophisticated mathematical techniques. As more telescopes around the world turned their attention to 3-Eye Atlas, the orbital solution began to sharpen and clarify. The object's hyperbolic trajectory became increasingly well-defined, with an eccentricity significantly greater than 1, confirming its interstellar origin beyond any doubt. But more importantly, the growing collection of observations began to reveal subtle deviations from a purely gravitational path. These deviations showed up as tiny residuals, small differences between where the object was predicted to be based on gravity alone and where it actually appeared in the telescopic images. At first, these residuals might have been dismissed as observational noise or minor measurement errors. But as the data accumulated, a pattern began to emerge that suggested something more interesting was at work. The most likely explanation for these residuals was that 3I Atlas was experiencing what astronomers call non-gravitational forces. Unlike the predictable pull of the sun's gravity, these forces arise from the object itself, perhaps from gas and dust being ejected as solar heating causes volatile materials to sublimate from the visitor's surface. These tiny jets of material, invisible to direct observation, can impart small but measurable accelerations that alter the object's trajectory in subtle but detectable ways. For astronomers familiar with comets, such non-gravitational forces are routine. Cometary nuclei are essentially dirty snowballs, mixtures of ice and rock, that begin to sublimate and outgas as they approach the sun. The escaping gas and dust create the beautiful tails that make comets so spectacular, but they also act like tiny rocket engines, gently pushing the comet away from its purely gravitational path. But 3I Atlas was supposed to be different. Early observations suggested it might be more like 1 Lua, a relatively inactive object that had shown no obvious signs of cometary activity, despite experiencing similar non-gravitational forces. The detection of subtle orbital deviations hinted that our third interstellar visitor might have its own surprises in store. As the orbital solution continued to improve with each new night of observations, astronomers began to anticipate something special. The object was approaching the inner solar system during a period of unusually high solar activity, with the sun experiencing one of its most active phases in years. Solar storms and coronal mass ejections were becoming increasingly common, filling the space around the sun with enhanced solar wind and magnetic turbulence. The stage was being set for a dramatic encounter between our interstellar visitor and our temperamental host star. The careful orbital calculations suggested that 3I Atlas would make its closest approach to the Sun during the peak of this solar activity, potentially triggering responses that had never been observed in an interstellar object before. But such dramatic events lay still in the future. For now, astronomers continued their patient work of measurement and calculation, gradually refining their understanding of the visitor's path, while watching carefully for any signs of the changes that the orbital residuals seemed to predict. Chapter 5. The Insane Moment. A sudden outburst in a stormy sun. The sun was angry. Not in any destructive or dangerous sense, but with the magnificent, tempestuous beauty that our star displays during the peak of its 11-year activity cycle. Solar flares erupted from its surface with increasing frequency, sending waves of charged particles racing across the solar system. Coronal mass ejections, vast bubbles of plasma and magnetic field lines, burst forth from the solar corona like cosmic soap bubbles, each one carrying the energy equivalent to billions of nuclear weapons, yet dispersing harmlessly across the vast distances of space. It was into this arena of stellar fury that 3I Atlas made its approach, following its hyperbolic trajectory toward a rendezvous with the inner solar system. For months, astronomers had been tracking the visitor's steady approach, watching it grow slightly brighter as it drew closer to the sun's warmth. Its behavior had been predictable, almost sedate. Just another point of light moving against the background stars, distinguishable from countless asteroids and comets, mainly by the mathematical signature of its interstellar origin. Then, in the span of just a few days, everything changed. Picture the first astronomer to notice the transformation. Perhaps it was during a routine photometric observation, carefully measuring the visitor's brightness to track its expected gradual brightening as it approached the sun. The measurement came back wrong, not just a little off, but dramatically, impossibly wrong. Where 3i Atlas should have been perhaps 10% brighter than the previous week, it was suddenly shining with 10 times its previous intensity. At first, there might have been doubt. Instrumental errors, calibration problems, atmospheric interference, any number of mundane explanations could account for such a dramatic change in brightness. But as confirmatory observations poured in from telescopes around the world, the reality became undeniable. 3i Atlas had undergone what astronomers call an outburst, erupting into activity with a suddenness and intensity that caught everyone by surprise. The timing was remarkable. Just hours before the outburst began, the Sun had unleashed one of its most powerful coronal mass ejections in months, a vast bubble of magnetized plasma that raced outward through the solar system at speeds exceeding 1,000,000 miles per hour. The shock front from this solar storm had swept past Mercury, engulfed Venus, and was racing toward Earth when it encountered our interstellar visitor, still millions of miles from its closest approach to the Sun. What happened next was unlike anything astronomers had observed before in an interstellar object. As the solar storm's shock front washed over 3a Atlas, the visitor's surface began to respond with dramatic intensity. Volatile ices that had remained frozen and stable during the object's journey through interstellar space suddenly found themselves subjected to an environment far more energetic than simple solar heating could provide. The enhanced solar wind density and magnetic field strength associated with the coronal mass ejection created conditions that triggered massive sublimation of the most volatile components of the visitor's surface: carbon monoxide and carbon dioxide. Normally stable even at the relatively warm temperatures of the inner solar system, began to sublime, rapidly under the influence of the enhanced particle bombardment and magnetic field interactions. As these gases escaped from the surface of 3i Atlas, they carried with them tiny particles of dust and larger fragments of the visitor's crust. What had been an invisible asteroid-like object suddenly sprouted a tenuous but rapidly expanding atmosphere of gas and dust. And as this newly formed coma expanded and interacted with the solar wind, it began to glow with the characteristic light of fluorescent gas molecules excited by solar ultraviolet radiation. The brightening was spectacular. In less than 48 hours, 3i Atlas went from being a faint telescopic object, visible only to dedicated observers, to something that could be spotted with modest amateur equipment. Its brightness increased by more than 1,000 times, transforming it from an unremarkable moving star into one of the most dramatic cometary displays visible from Earth. But the outburst brought more than just increased brightness. As gas and dust jetted away from discrete areas on the visitor's surface, these jets began to impart small but significant forces on the object itself. Picture a spinning top that suddenly begins to spout tiny streams of water from various points on its surface. The escaping water would not only make the top more visible, but would also begin to alter its rotation, causing it to wobble, and eventually tumble in complex ways. This is precisely what began to happen to 3i Atlas. The object's rotation, which had been stable and predictable throughout its long interstellar journey, suddenly became chaotic and complex. The visitor began to tumble, its brightness varying not just from the overall outburst activity, but also from the changing cross-sectional area. It presented to telescopic observers as different faces rotated in and out of view. The jets of gas and dust weren't distributed uniformly across the visitor's surface. Instead, they seemed to emerge from discrete active areas, perhaps regions where the crust was thinner or where the composition was particularly rich in volatile materials. As these jets fired in different directions and with varying intensities, they created a complex pattern of forces that overwhelmed the object's ability to maintain stable rotation. Spectroscopic observations during the outburst revealed a fascinating chemistry unlike anything seen in our solar system's native comets. The enhanced activity had liberated not just the expected water vapor and carbon dioxide, but also more exotic species, like carbon monoxide and complex organic compounds. The ratios of these different molecules suggested a composition that spoke of formation in an environment far colder and more chemically reducing than the region where our own solar system's comets were born. Perhaps most remarkably, the outburst appeared to be self-limiting. As the initial shock from the solar storm passed, and conditions around 3E Atlas returned to more normal levels, the intense activity began to subside. The visitor didn't continue to brighten indefinitely or fragment into pieces as some have done. Instead, it seemed to settle into a new equilibrium, still much more active than before the encounter, but no longer erupting with the dramatic intensity of those first few days. The correlation between the solar storm and the outburst was too precise to be coincidental. For the first time, astronomers were witnessing the direct interaction between an interstellar visitor and the dynamic environment of our solar system during a period of high solar activity. It was as if 3I Atlas had been waiting for just the right trigger to reveal its hidden volatile nature, remaining dormant throughout its long approach until the perfect confluence of solar fury and interstellar chemistry created conditions for its spectacular awakening. As the immediate drama of the outburst began to settle into a more manageable rhythm of observation and analysis, astronomers around the world began the careful work of understanding exactly what they had witnessed. The event had transformed 3I Atlas from an interesting but relatively quiet interstellar visitor into one of the most scientifically valuable objects ever to visit our solar system. Chapter 6. Light Curves in the Dark. Measuring brightness and calmly reading chaos in the quiet hours before dawn, when the sky is darkest and the atmosphere most stable, dedicated astronomers pursue one of their most meditative practices, photometry. Photometry. Armed with sensitive cameras and precise filters, they capture the subtle language of starlight, measuring brightness with an accuracy that would have seemed impossible to earlier generations of sky watchers. When 3I Atlas began its spectacular outburst, these patient observers found themselves documenting one of the most dramatic light shows ever recorded from an interstellar visitor. But rather than chaos, what emerged from their careful measurements was a beautiful story written in the grammar of brightness and time. A story that could only be read by those who knew how to listen to light itself. Picture the data as it accumulated night after night. Thousands of individual brightness measurements, each one a snapshot of the visitor's activity at a particular moment. Plotted against time, these measurements trace what astronomers call a light curve, a graph that captures the rhythm of an object's brightness variations with the precision of a cosmic heartbeat. The outburst light curve of 3I Atlas resembled a great wave rising from a calm sea. In the days before the solar storm encounter, the visitor's brightness had been remarkably stable, varying only slightly as different portions of its surface rotated in and out of view. Then came the sudden spike, a dramatic surge in brightness that peaked within hours of the coronal mass ejection's passage, rising to levels more than 1,000 times brighter than the pre-outburst baseline. But this wasn't a simple, sharp peak. Instead, the light curve revealed layers of complexity that spoke to the intricate physical processes at work on the visitor's surface. The initial brightening was accompanied by rapid fluctuations, brightness spikes and dips that occurred on timescales of hours, suggesting that different active regions on the object's surface were turning on and off in response to the changing conditions. As the immediate effects of the solar storm began to fade, the light curve entered a phase that astronomers found even more fascinating than the initial outburst. Rather than simply returning to its pre-event state, 3Gi Atlas settled into a pattern of complex variability. The object's brightness now oscillated with multiple periodicities, creating interference patterns that revealed the visitor was no longer rotating as a simple, stable body. The most obvious variation had a period of about 6.2 hours, likely the time it took for the object to complete one rotation about its primary axis. But superimposed on this main periodicity were longer-term variations with periods of days or weeks, suggesting that the visitor was processing like a wobbling top, tumbling chaotically, rather than spinning with the stable rotation it had maintained throughout its interstellar journey. These complex rotation patterns told a story of structural transformation. The outburst hadn't just released gas and dust from the visitor's surface. It had fundamentally altered the object's physical state. Thermal stresses, from the rapid heating and cooling during the event, had likely created new fractures and fissures in the surface material. The asymmetric forces from the escaping gas jets had overwhelmed the visitor's rotational stability, setting it tumbling in ways that would take months or years to settle into a new equilibrium. But perhaps the most poetic aspect of these light curve observations was how they transformed the apparent chaos of the outburst into something beautiful and comprehensible. Each brightness measurement represented light that had traveled across millions of miles of space, carrying with it information about conditions on the visitor's surface at the moment of emission. By catching and carefully measuring this light, astronomers were able to reconstruct events happening on a small world far from Earth with remarkable detail and precision. The photometric data revealed not just when the outburst occurred, but how it evolved over time. The rapid initial brightening was followed by a more gradual decline, punctuated by secondary peaks that suggested ongoing activity as different regions of the surface continued to respond to the changed conditions. Some of these secondary events appeared to correlate with the object's rotation period, indicating that certain active areas became more or less visible as the tumbling visitor presented different faces to observing telescopes. Color measurements added another layer to the story. By observing 3i Atlas through different filters that isolated specific wavelengths of light, astronomers could track how the visitor's spectrum evolved throughout the outburst. The initial brightening was dominated by scattered sunlight from newly liberated dust particles, giving the object a reddish hue characteristic of small rocky fragments. But as gas production increased, emission lines from excited molecules began to contribute their own characteristic colors to the overall spectrum. The most remarkable aspect of these light curve observations was their precision. Modern photometric techniques can measure brightness changes of less than 1%, allowing astronomers to detect subtle variations that reveal fine details about the physical processes at work. When applied to the dramatic brightness changes of 3I Atlas, this precision revealed structure within structure, patterns within patterns, that spoke to the complex interplay between the visitor's composition, structure, and the dynamic environment of the inner solar system. As weeks passed, and the initial excitement of the outburst began to settle into routine observation, the light curve of 3I Atlas continued to evolve. The object gradually faded from its peak brightness, but never returned to its pre-outburst state. Instead, it stabilized at a level several times brighter than before, suggesting that ongoing sublimation of volatile materials was maintaining a persistent low-level coma around the visitor. These patient photometric observations provided the foundation for everything else. Astronomers would learn about 3I Atlas and its remarkable transformation. The light curve data served as a roadmap, guiding more detailed spectroscopic and theoretical investigations by showing exactly when and how the visitor's activity evolved over time. Chapter 7. Invisible Hands. Jets, Radiation Pressure and Dust Sail Physics. Sometimes the most profound forces in the universe are completely invisible to our eyes. As 3I Atlas blazed across our telescopes in its magnificent outburst, a hidden drama was unfolding, a delicate interplay of forces so subtle that they could only be detected through their cumulative effects on the visitor's motion over weeks and months of careful observation. Picture this. Every photon of sunlight that strikes an object in space carries with it a tiny amount of momentum. For large, massive bodies like planets, this radiation pressure is utterly negligible, like trying to push a freight train with a feather. But for small particles of dust, freshly liberated from the surface of our interstellar visitor, sunlight becomes a significant force, capable of dramatically altering their trajectories and speeds. As 3I Atlas erupted in its solar storm-triggered outburst, it began to shed countless microscopic particles into the surrounding space. Each dust grain, no larger than the particles in cigarette smoke, suddenly found itself caught in the sun's intense radiation field. The constant bombardment of photons pushed against these tiny fragments with a force that, while individually minute, became collectively substantial when multiplied across billions of particles. But radiation pressure wasn't the only invisible hand at work. The escaping gas itself created jets. Streams of sublimating material that erupted from discrete points on the visitor's surface like tiny rocket engines. Unlike the symmetric radiation pressure that affects all particles equally, these jets were directional, asymmetric, and variable in their intensity and direction, as different regions of the surface became active or dormant. Imagine 3I Atlas as a cosmic Catherine wheel, spinning and tumbling while tiny jets of gas and dust fire from various points on its surface. Each jet imparts a small thrust in the opposite direction, following Newton's third law with the same faithfulness that governs rocket propulsion here on Earth. But unlike engineered rockets with their carefully controlled exhaust, these natural jets fire chaotically, sometimes strengthening, sometimes weakening, sometimes shutting off entirely as the surface composition and solar heating vary. The cumulative effect of these forces began to show up in the visitor's orbital motion, as subtle deviations from the purely gravitational path predicted by celestial mechanics. These non-gravitational accelerations were tiny, typically measured in millimeters per second squared, thousands of times smaller than Earth's gravitational acceleration. Yet, over the weeks and months of observation, these small forces accumulated into measurable changes in the visitor's position and velocity. Astronomers had seen such effects before, most notably in 1 Psi Oumuamua, our first confirmed interstellar visitor. That enigmatic object had shown clear signs of non-gravitational acceleration, despite displaying no obvious cometary activity. The mystery of Oumuamua's acceleration had sparked considerable debate, with explanations ranging from outgassing of nearly invisible amounts of gas to more exotic possibilities involving the object's shape and composition. With 3I Atlas, however, the source of the non-gravitational forces was beautifully clear. The spectacular outburst had provided direct visual evidence of the gas and dust production that drives such accelerations. Astronomers could watch in real time as jets of material erupted from the visitor's surface, and then measure how these jets altered the object's trajectory over the following weeks. The physics governing these interactions paint a picture of remarkable complexity hidden within apparent simplicity. As gas molecules sublime from the visitor's surface, they carry away energy in the form of heat, cooling the surface and potentially exposing fresh material underneath. The rotational story of 3I Atlas provided a unique window into processes that normally occur on timescales far too long for direct observation. By watching our interstellar visitor tumble and settle into its new equilibrium, astronomers gained insights into the fundamental physics of rotating bodies that apply throughout the solar system and beyond. From the asteroid belt to the icy bodies of the Kuiper belt, and perhaps to similar objects orbiting distant stars. Chapter 10. 3 travelers, 3 tales, 1I, 2I, and 3I side by side, in the grand narrative of our solar system's encounters with interstellar visitors. We now have 3 chapters written across just a few short years, each one telling a different story about the diversity of objects that wander between the stars, yet each one contributing to a larger understanding of what lies beyond our sun's gravitational embrace. Let us gather these 3 tales together, like old friends, sharing stories around a quiet fire, each visitor bringing its own unique perspective on the vast cosmic wilderness from which they came. First came 1I Oumuamua in 2017, the scout from the distant past, whose very name speaks to its role as a messenger from afar. This first confirmed interstellar visitor arrived like a riddle wrapped in an enigma, challenging our assumptions about what such objects should look like and how they should behave. Its extremely elongated shape, perhaps 10 times longer than it was wide, gave it the appearance of a cosmic cigar or, in more poetic moments, a needle threading through the fabric of space. Oumuamua was a visitor of contradictions. It showed no obvious signs of cometary activity, no visible coma, no dust tail, no spectroscopic signatures of sublimating gases, yet it exhibited clear non-gravitational acceleration, mysteriously speeding up as it rounded the sun, in a way that could only be explained by some form of outgassing too subtle for our telescopes to detect directly. Its surface appeared remarkably red in color, perhaps darkened and reddened by eons of exposure to cosmic radiation during its long journey through interstellar space. The mystery of Oumuamua sparked fierce debates and creative theories. Was it a fragment of solid hydrogen, slowly sublimating in the sun's warmth? A gossamer-thin light sail pushed by radiation pressure? A chunk of solid nitrogen, blown away from a Pluto-like world in another stellar system? Each theory attempted to reconcile the visitor's peculiar combination of properties, but none achieved universal acceptance. Oumuamua departed our solar system as mysteriously as it had arrived, leaving behind more questions than answers. Then, just 2 years later, came 2I Borisov, a visitor that seemed almost eager to demonstrate how different interstellar objects could be from one another. Where Oumuamua had been cryptic and contradictory, Borisov was refreshingly straightforward. It looked like a comet, behaved like a comet, and spectroscopic observations confirmed that it was indeed a comet in the classical sense. A mixture of ice and rock that began to sublime and develop a beautiful tail as it approached the sun. Borisov's composition was remarkable for how familiar it seemed, yet subtly different from our solar system's native comets. Its gas production rates and dust-to-gas ratios fell within the range of known comets, but detailed spectroscopic analysis revealed intriguing differences in the abundance of carbon monoxide and the isotopic ratios of various species. These subtle signatures suggested formation in an environment somewhat different from the region where our own comets were born, yet not so different as to be utterly alien. The visitor from the Borisov system, for that's how astronomers came to think of it, named after its discoverer, provided a reassuring demonstration that not all interstellar visitors would be as enigmatic as Oumuamua. Here was an object whose behavior could be understood and predicted using the same physical models that astronomers had developed for studying solar system comets. It was different, yes, but different in ways that expanded rather than challenged our fundamental understanding of how such objects work. Now we add the third tale to our collection, 3I Atlas, with its dramatic outburst and complex response to solar activity. This visitor combined aspects of both its predecessors while adding entirely new chapters to the story of interstellar objects. Like Oumuamua, it showed non-gravitational acceleration and revealed unexpected complexity in its behavior. Like Borisov, it demonstrated clear cometary activity with visible gas and dust production. But unlike either of its predecessors, 3I Atlas showed how dramatically an interstellar visitor could respond to the changing conditions and encounters in the inner solar system. The three visitors together paint a picture of remarkable diversity in the population of objects drifting between the stars. They suggest that planetary systems are constantly leaking material into interstellar space, fragments knocked loose by gravitational interactions, impacts, or stellar activity, each one carrying with it a sample of its birth environment's composition and formation history. Oumuamua might represent objects formed in the inner regions of other planetary systems, where rocky and metallic materials dominate, and volatile ices are scarce. Its unusual shape could result from formation processes or subsequent evolution very different from those that shaped objects in our own solar system. The mystery of its non-gravitational acceleration reminds us that even apparently simple objects can harbor surprises that challenge our theoretical understanding. Borisov likely represents the more familiar population of icy objects formed in the outer regions of planetary systems, similar to our own Kuiper Belt objects, but ejected into interstellar space by gravitational interactions with giant planets. Its behavior demonstrates that the basic physics of comet formation and evolution may be universal, even if the detailed chemistry varies from system to system. And 3I Atlas? Perhaps it represents objects formed in environments subject to more dramatic variability, regions where stellar activity, binary star interactions, or other dynamic processes created populations of icy bodies with enhanced volatile content and complex internal structures. Its explosive response to solar storm activity suggests a composition optimized for dramatic outbursts under the right conditions. Together, These three visitors have transformed our understanding of interstellar space from a sterile void to a rich ecosystem populated by refugees from countless other planetary systems. Each object carries within it the story of its birth world, the history of its ejection into interstellar space, and the record of its long journey through the galaxy before arriving at our doorstep. The statistical analysis of this small sample suggests that interstellar visitors may be more common than initially expected, arriving in our solar system perhaps once or twice per year, though most pass through undetected due to their small size or low activity levels. Improved survey capabilities and automated detection systems are beginning to reveal this previously hidden population, promising a rich harvest of interstellar discoveries in the years to come. As we prepare to bid farewell to our tale of three travelers, we can reflect on how these visitors have enriched our understanding, not just of interstellar space, but of planetary formation and evolution throughout the galaxy. They are cosmic time capsules, each one preserving samples of conditions that existed in alien stellar systems billions of years ago, now delivered to our laboratories and telescopes for detailed study. Chapter 13. Dust Trails and Night Sky Whispers. Could Earth see a meteor gift? In the quiet mathematics of orbital mechanics lies a beautiful possibility that dust grains, no larger than particles of flour, might carry messages between worlds across the vast darkness of space. When 3I Atlas outgassed near the Sun, it didn't just create the spectacular tail we photographed through our telescopes. Each molecule of water vapor that sublimated, each grain of dust that broke free from the warming nucleus, became a tiny spacecraft with its own trajectory, its own destiny. Most would drift into obscurity, but some, just some, might follow paths that intersect with Earth's orbit years or decades from now. Picture the delicate choreography involved. As our visitor rounded the Sun, jets of vapor carried dust particles away from the nucleus at speeds measured in meters per second. Gentle by cosmic standards, like dandelion seeds drifting on a summer breeze. But these particles didn't escape into empty space. They entered the complex gravitational field of the solar system, where the Sun's pull, the planet's subtle influences, and the radiation pressure of sunlight itself would shape their future paths. Each dust grain becomes a test particle in an enormous physics experiment. The smallest ones, perhaps 1/1000th of a millimeter across, feel radiation pressure most strongly. Photons from the Sun strike these microscopic flecks, imparting momentum that gradually pushes them outward, away from their parent comet. Scientists quantify this with the beta parameter, the ratio of radiation pressure to gravitational force, and for the tiniest grains, beta can exceed 1, meaning they're literally blown away by starlight. Larger particles, closer to the size of sand grains, resist radiation pressure better. Their trajectories stay closer to their parent's path, but they're not immune to perturbation. Over months and years, tiny forces accumulate. The Poynting-Robertson effect, as photons carry away orbital energy, gravitational perturbations from planets, even the subtle pressure of the solar wind itself. The result is a spreading cloud of debris, a dust trail that stretches along the visitor's orbital path but gradually disperses. Computer models show this dispersion as an elegant three-dimensional sculpture, narrow at first, then broadening like smoke from a stick of incense. The trail doesn't stay in a single plane but warps and twists as different particles respond to different forces. For most comets, these dust trails remain forever beyond Earth's reach. Their orbits are inclined to ours, or their distances too great, or their timing wrong. But occasionally, Very occasionally, the geometry aligns. A comet passes through the right position at the right time, leaving debris that will intersect Earth's orbit months or years later. The probability calculations for 3I Atlas are sobering. Preliminary analyses suggest that while dust trails will indeed form, their likelihood of intersecting Earth's orbit is extremely small. The visitor's hyperbolic trajectory carries it through regions of space that have little connection to our planet's annual journey around the Sun. But extremely small is not zero. And in astronomy, even unlikely events become inevitable given sufficient time, and it remains a significant if some future night were to bring us meteors from 3E Atlas, they would arrive with unusual characteristics. Their entry velocities would be higher than typical meteor shower particles, perhaps 40 or 50 kilometers per second. They would appear to radiate from a specific point in the sky, creating a radiant that moves slowly across the celestial sphere over the course of the night. More intriguingly, their composition would tell a story of interstellar origins. Spectroscopic analysis of meteor trains, the glowing trails left by particles burning up in our atmosphere, might reveal isotopic ratios that differ from solar system materials. The deuterium to hydrogen ratio, the mix of organic compounds, even the crystalline structure of dust grains, could preserve clues about formation conditions in another stellar system. Meteor observers would mount special campaigns if such an event seemed possible. Networks of all-sky cameras, deployed across continents, would watch for the characteristic streaks of light. Radio telescopes would listen for the ionization trails that meteors leave in their wake. Citizen scientists with handheld cameras would stand in dark fields, hoping to capture something never before seen. The physical remnants of interstellar space falling through our atmosphere like cosmic snow. The poetic justice of such an event appeals to something deep in the human spirit. For most of history, we could only look up at the stars and wonder about worlds beyond our reach. But interstellar visitors like 3I Atlas bring those distant realms to us, carrying physical samples across light years of emptiness. If even a few grains of their dust were to reach our atmosphere, we would hold in our instruments and our analysis the actual substance of alien worlds. The waiting time might be measured in decades. Dust trails evolve slowly, their particles following slightly different orbits, gradually spreading out like a cosmic river delta. Computer models suggest that if Earth intersecting debris exists at all, it would most likely arrive 30 to 50 years after the original passage, long enough for a generation of astronomers to retire and their students to take over the watch. But patience is fundamental to astronomy. We are accustomed to phenomena that unfold across timescales that dwarf human lives. The slow precession of planetary orbits, the 11-year solar cycle, the 26,000-year wobble of Earth's axis. All remind us that the universe operates on its own schedule, indifferent to our eagerness for immediate results. For now, the dust from 3I Atlas races outward from the Sun, each grain following its own trajectory into the growing twilight of interplanetary space. Some will be swept up by Jupiter or Saturn, adding infinitesimal amounts to those giant planets' ring systems. Others will drift toward the outer solar system, perhaps eventually crossing the heliopause to rejoin the interstellar medium from which their parent comet came. And a few, just possibly a few, might one day find their way to Earth, bringing with them the gentle fire of distant stars made manifest in our own night sky. These dust grains point backward in time, tracing paths that lead us to imagine distant origins. Let us travel there now, in the realm of possibility, to the stellar nurseries where our visitor might have been born. Chapter 14. Elsewhere, birth, ejection, and the long drift between stars long before our sun was even a whisper of gas and dust. In stellar systems whose names we will never know, the building blocks of 3 jutless were taking shape. Picture a young star, perhaps not so different from our sun in its infancy, surrounded by a disk of material that glows with the heat of formation. Within this disk, beyond the frost line where water can condense into ice, countless small bodies are accumulating, snowballs of frozen volatiles mixed with rocky debris, each destined to become a comet or asteroid in this alien solar system. The physics of planet formation operates by the same rules everywhere, but the outcomes can be strikingly different. Here, perhaps, giant planets migrated inward from their birth locations, their gravitational influence stirring the outer regions of the system into chaos. Or maybe close encounters between binary stars periodically disrupted the neat arrangement of orbits, sending showers of small bodies careening toward the edges of gravitational stability. In our own solar system, we see the evidence of such violent reshuffling in the late heavy bombardment, when Jupiter and Saturn's orbital migration sent comets and asteroids flying in all directions. Some crashed into the inner planets, creating the scarred surfaces we see on the Moon and Mars. Others were flung outward to populate the Kuiper Belt and Oort cloud. And some, just some, escaped entirely, joining the vast population of rogue objects that drift between the stars. For 3i Atlas, the moment of ejection might have come during such a migration event. Picture our visitor to be, perhaps just a few kilometers across, following a stable orbit in the outer reaches of its birth system. Then, over the course of a few thousand years, a giant planet's orbit begins to shift. Gravitational resonances build up like notes in a cosmic symphony, until finally something must give way. The ejection itself might have been surprisingly gentle, not a violent collision, but a gradual stretching of orbital eccentricity until escape velocity was reached. One day, our proto-comet found itself on a hyperbolic trajectory, racing away from the only gravitational environment it had ever known, climbing out of its star's gravity well toward the infinite darkness between worlds. The transition from bound to unbound is mathematically elegant. The moment when orbital eccentricity exceeds 1. When the familiar ellipse becomes a hyperbola opening toward infinity. But for the object itself, the change would have been imperceptible at first. Only gradually, over months and years, would the parent star have faded from a blazing beacon to just another point of light among countless others. Binary star systems might be particularly efficient at ejecting small bodies. When 2 stars orbit each other, their combined gravitational field creates regions of instability, zones where small objects can be repeatedly perturbed until they reach escape velocity. Computer simulations suggest that such systems might eject 10 times more comets than single stars like our Sun, contributing disproportionately to the interstellar population. Once free of its birth system, our future visitor began the longest journey imaginable. Millions of years of drift through the local interstellar cloud, following a trajectory determined by that ancient moment of ejection. The speeds are modest by cosmic standards, perhaps 20 to 30 kilometers per second relative to nearby stars, but sufficient to cross the gulf between stellar systems given enough time. During this interstellar voyage, our traveler aged in subtle ways. The interstellar radiation field, a weak but persistent bath of ultraviolet light and cosmic rays, gradually altered the surface chemistry, creating a dark, carbon-rich skin that would protect the interior from further radiation damage. Micrometeorites, tiny grains of dust, moving at relative speeds of tens of kilometers per second, sandblasted the surface, creating a regolith of fine particles mixed with the underlying ice and rock. The cold was absolute, perhaps 20 Kelvin above absolute zero, barely warm enough for helium to remain liquid. At such temperatures, most chemical reactions cease entirely, preserving whatever complex organic molecules might have formed during the early phases of planetary system evolution. In a sense, interstellar comets are time capsules, carrying pristine samples of conditions that existed during the first few million years of their birth systems. Our visitor might have encountered other stars during its journey, passing through the outer reaches of their gravitational influence, without significantly altering its trajectory. Each encounter would have been a brief astronomical event. A few thousand years when another star blazed brighter than the others, perhaps warming the surface by a few degrees before fading back into the stellar background. Carefully calibrated photometry, high-resolution spectra, and precise astrometric measurements will be archived in permanent repositories, available for future researchers to reanalyze with improved techniques and theoretical understanding. From these patient observers on Earth and in space, we lift our gaze toward more ambitious possibilities, imagining what we might do if we could reach out and touch these cosmic visitors ourselves. Chapter 17. If we could visit daydreams of interceptors and sailcraft in the quiet spaces between observation and imagination, engineers and mission planners dream of more intimate encounters with visitors from beyond our solar system. What if we could do more than simply watch these cosmic ambassadors race past? What if we could reach out across the vast distances and touch them, sample them, learn their deepest secrets through direct contact, rather than distant light? The challenges are magnificent in their scope. Interstellar visitors approach our solar system with velocities that dwarf anything achieved by human spacecraft. While our fastest planetary probes cruise at perhaps 20 kilometers per second, 3I Atlas swept past the Sun at more than 40 kilometers per second relative to our star. Traditional rocket propulsion, even with gravitational assists from multiple planets, struggles to match such speeds. Consider the Comet interceptor mission, already approved by the European Space Agency and scheduled for launch in the coming decade. This elegant concept places a spacecraft at the L2 Lagrange point, 1.5 million kilometers from Earth, where it waits patiently for a suitable target to be discovered. When astronomers identify a promising long-period comet, or, if we're fortunate, an interstellar visitor, the spacecraft can deploy from its parking orbit to attempt an intercept. The mission architecture has a dreamlike quality. Rather than launching directly toward a known target, we launch toward a point in space and time, trusting that the universe will eventually provide an appropriate destination. It's a strategy that requires remarkable faith in both astronomical discovery and mission planning, but it transforms seemingly impossible intercepts into merely very difficult ones. Solar sailing offers another pathway into these deep space encounters. Instead of carrying chemical fuel, solar sails harvest momentum from sunlight itself, using the gentle but persistent pressure of photons to accelerate gradually over long periods. A sail deployed near the sun, where solar intensity is greatest, could potentially reach velocities of several hundred kilometers per second, fast enough to pursue even the swiftest interstellar visitors. Picture such a craft. Gossamer thin, perhaps kilometers across when fully deployed, catching starlight like a cosmic spiderweb. The technology is no longer science fiction. Several small solar sails have already flown in space, demonstrating the basic principles. But scaling up to interstellar intercept missions would require advances in materials, science, deployment mechanisms, and attitude control that push current capabilities to their limits. The navigation challenges alone are breathtaking. Unlike planetary missions, where targets follow predictable orbits over decades-long flight times, interstellar visitors appear with little warning and follow trajectories that may be poorly known. Flight planners would need to design adaptive trajectories that can respond to updated orbital solutions as the target's path becomes better understood. Quick-draw missions represent the extreme end of this spectrum, spacecraft designed for rapid assembly and launch in response to newly discovered target. The concept mirrors emergency response systems on Earth, with standardized spacecraft components waiting in warehouses, ready for final integration once a destination is identified. Launch vehicles would be kept on standby alert, like fire trucks waiting for the alarm. But even the most optimistic scenarios involve flight times measured in years. A solar sail launched in response to 3I Atlas discovery might have reached the visitor just as it was leaving the inner solar system, a brief encounter with an object already racing toward interstellar space. The science return would be compressed into a few hours or days of close approach, demanding instruments capable of rapid, autonomous observation and analysis. The scientific payoff from such a mission would be transformative. Remote spectroscopy reveals molecular composition, but direct sampling could determine isotopic ratios with exquisite precision, map spatial variations across the nucleus surface, and detect trace compounds invisible to Earth-based telescopes. High-resolution imaging could resolve surface features smaller than a meter, revealing the texture and structure of materials formed in another stellar system. Consider the instruments such a spacecraft might carry: mass spectrometers to analyze gas and dust composition, cameras to document surface features and outgassing patterns, magnetometers to study any intrinsic magnetic field or interaction with the solar wind. Each instrument would need to operate autonomously, since communication delays mean that real-time control from Earth is impossible during the brief encounter phase. Dust collection presents particularly tantalizing possibilities. Aerogel collectors, like those flown on the Stardust mission to Comet Wild 2, could capture particles for eventual return to Earth. The technology for interstellar sample return remains far beyond current capabilities, but the samples themselves would be scientific treasures beyond measure. Actual atoms and molecules from another stellar system, available for analysis in terrestrial laboratories. Multiple spacecraft in formation could provide different perspectives on the same encounter, perhaps with one focusing on nucleus imaging, while another studies the coma and tail development. Communication between spacecraft would create a distributed observation network, multiplying the scientific return from these brief encounters. The psychology of such missions appeals to something fundamental in human nature: the desire to explore, to touch, to understand through direct experience rather than distant observation. Robotic spacecraft become our emissaries to these alien worlds, carrying human curiosity across impossible distances to worlds we may never visit ourselves. Funding and political support for such ambitious missions would require sustained international cooperation across decades-long development timescale. The success of projects like the International Space Station, and the James Webb Space Telescope demonstrates that such cooperation is possible. But interstellar intercept missions would push these collaborative models into new territory. Risk assessment becomes both more critical and more difficult for interstellar intercept missions. Unlike planetary missions, where decades of successful precedents provide confidence in mission design, intercepting fast-moving visitors from unknown origins involves fundamental uncertainties about target properties, encounter dynamics, and operational environments. Yet the dream persists, refined by each new discovery and technological advance. Engineers continue to design more capable solar sails, more efficient propulsion systems, more sophisticated autonomous spacecraft. The gap between current capabilities and mission requirements shrinks slowly but steadily, driven by the same curiosity that motivates our telescopic observations. Whether we visit or simply watch, every story of cosmic discovery eventually leads to the same quiet destination, the archives where data becomes memory, and observations transform into lasting knowledge. Chapter 18. Fading Footsteps. Archiving memory and the long goodbye there. Comes a moment in every astronomical discovery when the active observing phase draws to a close, when the telescopes turn toward new targets, and the excitement of real-time investigation settles into the quieter work of long-term analysis and preservation. For 3i Atlas, this transition is already underway. Our visitor, growing fainter with each passing month, racing back toward the interstellar medium from which it came. But the story doesn't end with the last photons captured by our detectors. In the digital repositories of modern astronomy, observations become artifacts of permanent scientific value, carefully catalogued and preserved for future researchers who may ask questions we haven't yet learned to formulate. Picture the data centers, where these observations find their final homes. Climate-controlled facilities where arrays of storage devices maintain perfect copies of every spectrum, every image, every measurement. The transition from active observation to archival science has its own poetry, transforming fleeting moments of discovery into enduring resources for investigation. The process of data curation involves far more than simple storage. Each observation must be accompanied by detailed metadata, information about telescope configurations, atmospheric conditions, calibration procedures, and data processing methods. Without this context, raw astronomical data becomes nearly meaningless, like musical notes without tempo or key signatures. Consider the detective work required to interpret observations made decades ago. Archive scientists must reconstruct its archaeological work, applied to relatively recent history, uncovering the methodology and assumptions embedded in data collected by previous generations of astronomers. For 3i Atlas, this archival process is still in its early stages. The most recent observations are being processed through standard pipelines, their photometry and astrometry extracted using well-tested algorithms. But as the visitor fades and observing campaigns conclude, attention will shift from gathering new data to extracting maximum scientific value from existing observations. Cross-mission comparisons become possible only through careful archival work. How does 3i Atlas compare to Oumuamua and 2i Borisov? The answer requires homogeneous reprocessing of data from different telescopes, different observing campaigns, different analysis techniques. Archival astronomers develop expertise in translating between instrumental systems, creating unified datasets that enable meaningful comparisons. The International Astronomical Union maintains registries of interstellar objects, assigning formal designations and tracking basic orbital and physical parameters. But the real scientific value lies in the detailed observations archived at individual observatories and data centers. These repositories become the raw material for future theoretical investigations, population studies, and comparative analyses. Machine-readable formats ensure that archived data remains accessible as computer technologies evolve. The astronomical community has learned hard lessons from early digital storage formats that became obsolete within decades, leaving valuable observations stranded on unreadable media. Modern archival systems emphasize open standards and periodic migration to newer storage technologies. Version control becomes crucial when dealing with refined data products. Orbital solutions improve as more observations become available, and better analysis techniques are developed. Photometric calibrations are updated as systematic errors are understood. Spectroscopic reductions benefit from improved atomic and molecular databases. Each iteration must be preserved alongside its predecessors, creating genealogies of scientific understanding. The democratization of astronomical data through open archives has transformed research practice. Graduate students can now access the same datasets used by major research groups, enabling independent verification of results and exploration of alternative analysis approaches. This openness accelerates scientific progress while building confidence in published conclusions. But accessibility brings its own challenges. Archive interfaces must balance completeness against usability, providing both simple query tools for casual users and sophisticated search capabilities for expert researchers. Documentation must serve both pedagogical and reference functions, explaining basic concepts while preserving technical details that specialist users require. The temporal aspect of archival science creates unique opportunities. Observations separated by months or years can reveal variability patterns invisible in individual datasets. Light curves that seemed chaotic in real time may show clear periodicity when viewed retrospectively with complete phase coverage. The archive becomes a time machine, enabling researchers to revisit past events with the benefit of hindsight. Quality assessment takes on special importance for interstellar visitor observations, which often push instruments to their sensitivity limits. Bad weather, instrumental problems, and processing errors that might be acceptable for routine survey work become critical limitations when studying faint, rapidly moving targets. Archive quality flags must capture these subtleties, warning future users about potential problems, while preserving marginally useful data that might contribute to ensemble analyses. The software tools used for data analysis become part of the archival ecosystem. Code repositories preserve not just the algorithms used for reduction and analysis, but also version histories, configuration files, and example usage patterns. Reproducible science requires this level of detail, enabling future researchers to understand exactly how archived results were obtained. Educational outreach represents another dimension of archival value. High-quality datasets from interstellar visitors become case studies for graduate courses in observational astronomy, providing concrete examples of detection techniques, orbital determination methods, and spectroscopic analysis. The archives serve multiple generations of students who may never observe such objects directly, but can learn from preserved examples Legacy planning acknowledges that today's cutting-edge observations will eventually become historical curiosities, superseded by more sensitive instruments and refined techniques. But this progression doesn't diminish their value. Early observations of interstellar visitors establish baseline properties against which future discoveries can be compared, documenting the evolution of observational capabilities alongside scientific understanding. The quiet satisfaction of archival work appeals to a different temperament than the excitement of discovery phase astronomy. Archive scientists find meaning in the careful preservation of knowledge, in building infrastructure that serves research communities across decades, in ensuring that today's discoveries remain accessible to tomorrow's investigators. With the data safely preserved and the observations archived, we prepare for the most intimate part of our journey, drifting alongside our cosmic visitor as it returns to the darkness between stars. Chapter 19. Drift and Dream. A guided cosmic wind down. Close your eyes now and drift with me into the deepest quiet of space, where our story finds its most peaceful conclusion. We are floating alongside 3I Atlas, no longer the bright visitor that caught our telescope's attention, but a quiet wanderer once again returning to the spaces between stars. The sun, that blazing furnace that warmed our traveler into its spectacular outburst, has shrunk to just another point of light, brighter than the others, yes, but no longer the dominant force in this small world's existence. Feel the profound silence here, beyond the reach of Earth's atmosphere, beyond the whisper of solar wind, in the growing twilight of interplanetary space. There is no sound as we understand it, yet there is presence. The gentle radiation pressure of distant starlight, the almost imperceptible tug of gravity from worlds we left behind, the soft dance of charged particles spiraling along magnetic field lines. Our companion nucleus rotates slowly as we watch, its surface scarred by the thermal stresses of its solar encounter. Patches of dark, carbon-rich material alternate with brighter exposures where sublimation carved away protective layers, revealing the ancient ice beneath. This is a world that remembers formation temperatures in a stellar system whose name we will never know, carrying isotopic signatures of processes that occurred when our own sun was not yet born. The coma that once surrounded our traveler like a delicate veil has largely dissipated now, its water vapor and carbon monoxide scattered into the vacuum of space. But traces remain, individual molecules catching and reflecting sunlight, creating the faintest possible glow around the nucleus. It is beautiful in its subtlety, this last breath of activity before the return to interstellar dormancy. As we drift together through this cosmic quiet, let us gather the threads of our journey one more time, holding them gently like treasured memories. We remember the moment of recognition, when algorithms deep in the Atlas survey first noticed something moving against the stellar backdrop with the wrong kind of motion. Too fast, too inclined, carrying the mathematical signature of interstellar origins. In that automated detection lay the culmination of decades of patient sky surveys, computer systems tirelessly comparing images night after night, waiting for exactly this kind of cosmic gift. We followed the careful choreography of orbital determination, watching uncertainty shrink as observations accumulated. As the visitor's hyperbolic path emerged from the noise of measurement error and systematic bias, each telescope, pointing, refined our knowledge by fractions of an arcsecond. Each spectroscopic observation revealed new molecular signatures. Each photometric measurement mapped the rotation and outgassing patterns that told stories of internal structure and composition. The outburst itself remains one of our most vivid memories. That sudden brightening that transformed a faint point of light into something spectacular enough to capture in amateur telescopes around the world. We understood it as a solar storm passed by, the sun's magnetic tantrum, adding energy to the warming and sublimation processes that were already beginning as our visitor approached perihelion. We learned to read light curves like poetry, watching brightness variations trace out rotation periods and activity cycles. Spectroscopy became our translator, converting wavelengths of light into molecular abundances, isotope ratios, and temperature estimates. The deuterium to hydrogen ratio whispered of formation conditions in stellar nurseries light years distant and millions of years past. Jupiter's gravitational influence reminded us that even in the vast emptiness of space, everything affects everything else. That prediction requires accounting for forces both large and small, obvious and subtle. The Monte Carlo ensembles of possible trajectories taught us to embrace uncertainty as a fundamental feature of the universe rather than a limitation of our measurements. We marveled at the space weather that provided our visitors' backdrop. Coronal mass ejections racing outward from the sun. The solar wind's variable density and magnetic field, creating an ever-changing ocean through which our travelers swam. The heliosphere revealed itself as a living, breathing entity, pulsing with the 11-year heartbeat of solar activity cycle. Now, as we float in this growing darkness, watching our companion fade back toward interstellar invisibility, we carry with us the profound satisfaction of questions asked and partially answered. We have touched, however briefly, a piece of another stellar system. We have held in our instruments and our mathematics a visitor that carries physical samples of alien worlds across the impossible distances between stars. The dust trails that our visitor left behind continue their own journeys, each grain following its own trajectory through the outer solar system. Perhaps, just perhaps, some will find their way to Earth in decades to come, bringing with them the gentle fire of meteors that connect our night sky to distant stellar nurseries. The archives preserve our observations, carefully catalogued and maintained for future researchers who will ask questions we haven't yet learned to formulate. The data become more than numbers. They become memory, testament to a moment when two worlds briefly shared the same sky. Feel yourself breathing with the rhythm of cosmic time now, where moments stretch into years and years, compress into heartbeats. Our visitor continues its ancient journey, carrying within its frozen heart the chemistry of star formation, the isotopes of planetary system evolution, the complex organic molecules that form in the cold, quiet between worlds. The sun's light grows weaker as we drift outward together, but it will never completely fade. Even in the depths of interstellar space, our star will remain visible to our traveler. A fifth magnitude star in the constellation Cassiopeia, one bright point among the thousands that fill the night sky of wandering worlds. Other stars await in the distance: Proxima Centauri, Wolf 359, Barnard's star, each eventually growing brighter as eons pass, and galactic rotation carries them into new configurations. Our visitor will witness stellar encounters that span geological time, watching binary systems evolve, seeing new stars born from molecular clouds, perhaps even finding temporary gravitational capture around some future solar analog. But for now, in this perfect moment of cosmic quiet, we drift together in the growing darkness. Two tiny worlds sharing the vast silence between stars. The universe is immense and ancient and filled with wonders we can barely imagine. But tonight, right now, It is also gentle, peaceful, and touched with the quiet satisfaction of curiosity, rewarded and mystery partially unveiled. Sleep now, as worlds sleep between the stars, carrying dreams of distant suns and the patient certainty that morning always comes, even in the deepest darkness of space. And so, as we close this chapter beneath the quiet stars, we're reminded that every story the universe offers is both an answer and a question, guiding us deeper into wonder. If this journey has stirred your curiosity, you're welcome to stay. There are always more paths to explore, more mysteries to unfold, and more quiet hours to share together. I am the Sleeping Professor, your companion through these quiet journeys. You're watching The Sleeping Professor, a place where we explore the universe slowly, carefully, and always with wonder. Until we meet again beneath the stars, may your night be calm, and your thoughts wide as the sky. Chapter 20. The Silence After Motion. There comes a moment in every great astronomical encounter when the data stops arriving. Not suddenly, not dramatically, but quietly, like the last note of a song fading into the air, leaving only the memory of its sound. For weeks, perhaps months, 3i Atlas has been the center of attention. Telescopes across the world have turned their mechanical eyes toward it. Spectrographs have dissected its light. Computers have tracked its motion, frame by frame, pixel by pixel. It has been analyzed, and eventually, the observations stop. This is the phase astronomers know intimately, though few outside the field ever witness it. It is the silence after wonder. The moment when the universe, which for a brief time felt close enough to touch, withdraws once more into distance. The telescopes are reassigned. New targets are queued. The observation logs are closed, time-stamped and filed. The researchers who stayed up through cold nights, who coordinated across time zones, who held their breath as each new spectrum arrived, they too begin to step away. Not because the comet is no longer interesting, but because it is no longer there, at least not in the way it was. It has slipped beyond the reach of our instruments, back into the vastness from which it came. And in its wake, it leaves something strange, a kind of melancholy. There is a rhythm to discovery that mirrors grief. First, the thrill of the new, then the rush to understand, then the slow realization that the moment is finite. That all things observed are also, inevitably, things lost. The comet doesn't care, of course. It continues its journey, indifferent to whether we are watching. But for those who watched, the absence is felt. They return to their offices, their labs, their homes. They begin the long work of reduction, converting raw images into calibrated data, formatting tables, writing drafts. The comet, once a living presence in the night sky, becomes a set of numbers in a spreadsheet, a curve on a graph, a footnote in a paper not yet published. This is not cold or mechanical. It is simply the way science metabolizes wonder. It takes the raw experience of the universe and distills it into something that can be shared, tested, and remembered. But the silence remains. In the days following the final observation, some researchers find themselves still checking the data feeds, just in case. Just to see if there's one more image, one more measurement, one more glimpse before it's truly gone. There never is. And so they learn once again what every astronomer must learn, that the universe gives us only brief windows, that every comet, every supernova, every fleeting alignment is a gift on loan, never to be possessed, only witnessed. This is the paradox of astronomy. The closer you look, the more you realize how much you are losing. Every observation is also a farewell, but even in silence, traces remain. The Wolvermorn. There de more beat var dozy is as it members say. Not in the sky. No, The sky is empty now where 3i Atlas once burned, but in the data, in the archives, in the minds of those who saw it and thought. We were here. We noticed. We tried to understand. And perhaps that is enough, because while the comet may be gone, its echo is not. It lingers in hard drives, in cloud servers, in the metadata of 1,000 images. It lives on in preprints submitted to journals, in conference talks not yet given, in questions still being asked by students who will never see the comet themselves, but who will spend years studying what it left behind. The silence after motion is not truly silence. It is transformation. The comet has passed from the realm of observation into the realm of memory. And memory, unlike light, does not fade according to the inverse square law. Memory bends, it deepens, it becomes story. So we step back from the telescopes. We close the observation logs. We let the night sky return to its usual catalogue of stars, unnamed, uncounted, undisturbed. And in that quiet, we prepare for what comes next. Not the end of the story, but the beginning of its second life. Chapter 21. Echoes in the Archive. If you were to visit the vast digital archives of modern astronomy, servers scattered across continents, humming quietly in climate-controlled rooms, you would find something extraordinary. You would find light. Not the light itself, of course. That has long since dissipated, absorbed by mirrors and detectors, converted into electrical signals and filed away. But its shape remains, its signature. The faint trace of photons that travelled for millions of years, only to be caught, counted and stored as ones and zeros. This is where 3i Atlas lives now. Not in the sky, not in motion, but in stillness. A stillness more permanent than stone. The images taken during its passage have been archived. The spectra have been catalogued. The orbital parameters have been refined and entered into databases maintained by institutions whose names sound like incantations. The Minor Planet Center, the NASA Exoplanet Archive, the European Space Agency's data repositories. These archives are not dusty shelves in forgotten libraries. They are living systems, constantly queried, cross-referenced, reanalyzed. Data from 3i Atlas will be downloaded by researchers who were children when it passed. It will be compared to comets not yet discovered. It will be fed into models that do not yet exist. This is the strange immortality of astronomy. The comet itself may never return. It may drift for eons through interstellar space, untouched and unseen. But its record, the light it reflected, the atoms it shed, the trajectory it traced, those things will persist as long as humanity keeps its archives alive. And archives, unlike comets, are patient. There is a term in data science, future-proofing. It refers to the practice of storing information in such a way that it remains accessible and useful even as technology evolves. Astronomers have been doing this for centuries, long before the term existed. Ancient star catalogues, scribbled by hand in Babylon, Athens, Baghdad, are still referenced today. Photographic plates from the early 1900s are scanned and digitized, revealing asteroids that no one noticed at the time. Every observation, no matter how mundane it seemed in its moment, carries the potential for rediscovery. 3i Atlas is no different. Right now, somewhere, an algorithm is sifting through its data. A graduate student is writing code to extract trace elements from its spectra. A simulation is running, testing whether its trajectory could have brought it through the Oort cloud of another star system billions of years ago. The comet is gone, but its echo is loud, and it will grow louder over time, because data, unlike memory, does not decay. It does not fade with the telling. It sharpens. As our tools improve, as our models become more sophisticated, we will see details in the archived observations that were invisible when they were first taken. We will notice features in the dust tail that were dismissed as noise. We will detect molecular signatures that our spectrographs were barely sensitive enough to record. We will trace its origin with greater precision, perhaps even identifying the star system it once orbited. All of this will happen in silence. No new telescopes will turn toward 3I Atlas. No new images will be captured, but the data, unchanging, patient, will continue to yield answers long after the questions have been forgotten. This is the continuity of science. Not a straight line, but a spiral. Each generation revisits the observations of the last, asking new questions, finding new meanings. The archive is not a tomb. It is a garden, tended by minds separated by years, by continents, by languages, but united in curiosity. And so 3I Atlas endures, not as rock and ice, not as light and motion, but as information, structured, searchable, eternal, in the only way the universe allows, through human effort and intention. One day, centuries from now, someone may query an archive and find it. They may not know its name. They may not care about the excitement of its discovery, but they will see its data and they will learn something new. Perhaps they will use it to refine models of planetary formation. Perhaps they will trace its chemistry back to the molecular cloud where it was born. Perhaps they will simply marvel at the fact that their ancestors noticed this tiny speck of ice and decided it was worth recording. And in that moment, across the gulf of time, the observation will complete its purpose. Not when it was taken, but when it was understood. Because data is not just storage, it is conversation. A message written by one generation to be read by another. A way of saying, we saw this, we thought it mattered, we preserved it for you. And as long as that conversation continues, as long as someone, somewhere, is still asking questions, the light of 3I Atlas will never truly fade. It will simply transform. From photons into pixels, from pixels into meaning, from meaning into the quiet, enduring knowledge that we are part of something larger than ourselves. A lineage of watchers, a continuity of wonder. And while its light fades in our skies, its signal still travels inward, into our instruments, into our minds, and into the long memory of a species that refuses to let the universe pass unnoticed. Chapter 22. Messages in Motion. What 3I Atlas? 3I Atlas did not arrive with a message written on its surface. It carried no inscriptions, no signals, no intent. It was simply matter in motion. An object governed by gravity and momentum, oblivious to the fact that it was being watched. And yet, we treated it like an envoy. We analyzed its light as if it were language. We studied its composition as if it were a biography. We traced its trajectory as if it were a story with a beginning, middle, and end. In doing so, we revealed something profound, not about the comet, but about ourselves. Because the way we engage with the unknown is never neutral. It is always colored by hope, fear, curiosity, and longing. We do not simply observe, we interpret, we project. We ask not only what is this, but what does this mean for us? Consider the moment 3I Atlas was confirmed as interstellar. We were those, we be, phase what, full. There was excitement, yes, but also something deeper, a kind of existential thrill. Because if an object could travel from another star system into ours, then the universe was not compartmentalized. The boundaries we imagined, between here and there, between our story and the cosmos, were suddenly permeable. We were no longer isolated. And that realization carried weight. For most of human history, the stars were distant and unreachable. The night sky was a dome, painted with lights we could name, but never touch. We built myths around them, yes, but those myths were always ours. Projections of our own fears and dreams onto an unchanging backdrop. But interstellar objects shatter that illusion. They arrive from somewhere else. They prove that the universe is not static but dynamic. That matter flows between stars, that the galaxy is a network, vast and interconnected, and that we are part of it, not as the center, but as one node among billions. This is humbling, but it is also comforting. Because if the universe is a network, then we are not alone in our wonder. Somewhere, perhaps, another world has watched objects pass through their skies and asked the same questions we are asking now. They may have built telescopes. They may have catalogued and archived. They may have felt the same quiet melancholy when the visitor faded from view. Or they may not. The universe does not require witnesses, but the fact that we choose to witness, that we turn our instruments and our attention toward fleeting specks of ice and stone, says something essential about what it means to be human. We are meaning makers. We take raw phenomena, an orbit, a spectrum, a glint of reflected sunlight, and we weave them into narrative. We name the nameless. We catalogue the chaos. We ask questions not because we expect the universe to answer, but because asking is how we orient ourselves in the vastness. 3i Atlas did not come to teach us, but in watching it, we taught ourselves. We learned once again that discovery is a communal act. The comet was not found by one person, but by a network. Telescopes linked across continents, researchers sharing data in real time, amateurs and professionals collaborating without borders. We learned that the universe rewards patience. The comet was not dramatic. It did not blaze across the sky. It moved slowly, faintly, requiring careful observation and long exposure times. And yet, those who waited were rewarded with knowledge. We learned that wonder does not require proximity. 3i Atlas was never closer than the orbit of Mars. It never posed a threat. It was simply passing through. And yet, we watched it as if it were a guest in our home, curious, cautious, and a little bit hopeful that it might stay longer. And we learned, perhaps most importantly, that the unknown is not something to fear. It is something to study, to document, to honor. Because every object from beyond our system carries within it the history of places we will never see. It is a fragment of another story, one that intersects with ours for only a brief moment before diverging once more. And in that intersection, we find meaning. Not because the comet gives it to us, but because we create it, through observation, through curiosity, through the simple act of paying attention. This is what 3i Atlas teaches. Not about comets, not about interstellar chemistry or orbital mechanics, but about us. About our need to connect with something larger than ourselves. About our refusal to let the universe remain anonymous. About the strange, stubborn hope that drives us to point telescopes at faint smudges of light and say, "I see you. I want to understand." And in that moment, between observation and understanding, between question and data, we become something more than isolated beings on a small planet. We become participants in a story that began long before us and will continue long after. A story written not in words, but in motion, in light. In the quiet, persistent act of noticing. And as 3i Atlas fades beyond the reach of our instruments, that story does not end. It simply shifts from questions about what it is. We drift toward questions about what we are, and in the space between those questions, we find not answers, but something better. We find wonder. Chapter 22. Messages in Motion. What 3i Atlas? 3i Atlas did not arrive with a message written on its surface. It carried no inscriptions, no signals, no intent. It was simply matter in motion. An object governed by gravity and momentum, oblivious to the fact that it was being watched. And yet, we treated it like an envoy. We analyzed its light as if it were language. We studied its composition as if it were a biography. We traced its trajectory as if it were a story with a beginning, middle, and end. In doing so, we revealed something profound, not about the comet, but about ourselves. Because the way we engage with the unknown is never neutral. It is always colored by hope, fear, curiosity, and longing. We do not simply observe, we interpret, we project. We ask not only what is this, but what does this mean for us? Consider the moment 3i Atlas was confirmed as interstellar. We were souls, we be, phase what, fall. There was excitement, yes, but also something deeper, a kind of existential thrill. Because if an object could travel from another star system into ours, then the universe was not compartmentalized. The boundaries we imagined, between here and there, between our story and the cosmos, were suddenly permeable. We were no longer isolated, and that realization carried weight. For most of human history, the stars were distant and unreachable. The night sky was a dome, painted with lights we could name, but never touch. We built myths around them, yes, but those myths were always ours. Projections of our own fears and dreams onto an unchanging backdrop. But interstellar objects shatter that illusion. They arrive from somewhere else. They prove that the universe is not static, but dynamic. That matter flows between stars, that the galaxy is a network, vast and interconnected, and that we are part of it, not as the center, but as one node among billions. This is humbling, but it is also comforting. Because if the universe is a network, then we are not alone in our wonder. Somewhere, perhaps, another world has watched objects pass through their skies and asked the same questions we are asking now. They may have built telescopes. They may have catalogued and archived. They may have felt the same quiet melancholy when the visitor faded from view. Or they may not. The universe does not require witnesses, but the fact that we choose to witness, that we turn our instruments and our attention toward fleeting specks of ice and stone, says something essential about what it means to be human. We are meaning makers. We take raw phenomena, an orbit, a spectrum, a glint of reflected sunlight, and we weave them into narrative. We name the nameless. We catalogue the chaos. We ask questions not because we expect the universe to answer, but because asking is how we orient ourselves in the vastness. 3i Atlas did not come to teach us, but in watching it, we taught ourselves. We learned once again that discovery is a communal act. The comet was not found by one person, but by a network. Telescopes linked across continents, researchers sharing data in real time, amateurs and professionals collaborating without borders. We learned that the universe rewards patience. The comet was not dramatic. It did not blaze across the sky. It moved slowly, faintly, requiring careful observation and long exposure times. And yet, those who waited were rewarded with knowledge. We learned that wonder does not require proximity. 3i Atlas was never closer than the orbit of Mars. It never posed a threat. It was simply passing through. And yet, We watched it as if it were a guest in our home, curious, cautious, and a little bit hopeful that it might stay longer. And we learned, perhaps most importantly, that the unknown is not something to fear. It is something to study, to document, to honor. Because every object from beyond our system carries within it the history of places we will never see. It is a fragment of another story, one that intersects with ours for only a brief moment before diverging once more. And in that intersection, we find meaning. Not because the comet gives it to us, but because we create it, through observation, through curiosity, through the simple act of paying attention. This is what 3i Atlas teaches. Not about comets, not about interstellar chemistry or orbital mechanics, but about us. About our need to connect with something larger than ourselves. About our refusal to let the universe remain anonymous. About the strange, stubborn hope that drives us to point telescopes at faint smudges of light and say, "I see you. I want to understand." And in that moment, between observation and understanding, between question and data, we become something more than isolated beings on a small planet. We become participants in a story that began long before us and will continue long after. A story written not in words, but in motion, in light. In the quiet, persistent act of noticing. And as 3i Atlas fades beyond the reach of our instruments, that story does not end. It simply shifts from questions about what it is. We drift toward questions about what we are, and in the space between those questions, we find not answers, but something better. We find wonder. Chapter 24: Cosmic Memory and the Fragile Continuum. There is a question that lingers at the edge of all astronomical observation, unspoken but ever present. Will anything we see be remembered? Not by us. We know that our individual memories are fleeting, vulnerable to time and biology. But by the universe itself, does the cosmos remember its own events? Does it carry within it some trace of every comet that has ever passed, every star that has ever flared, every collision and coalescence that has ever occurred? Or does it simply move forward, indifferent, erasing as it creates? The answer, like most things in astronomy, is both. The universe does not remember in the way we do. It has no mind, no consciousness, no archive of emotional significance. But it does preserve. Every event leaves a mark. When 3i Atlas passed through our solar system, it shed molecules into the space between planets. Dust particles, atoms of carbon and oxygen and nitrogen, stripped away by solar wind and radiation. These particles did not vanish. They dispersed. They joined the faint haze of interstellar matter that drifts through the galaxy. Unnoticed, uncounted, but undeniably there. In that sense, the comet is still here. Not as a coherent object. Not as something we can point to and say, "There it is," but as fragments, distributed across distances so vast that they may never be collected again. This is the universe's version of memory, persistence through dispersal. But there is another kind of memory at work. One more fragile and yet more powerful, human memory. Because, while a comet's atoms may scatter into the void, the fact that we noticed them, that we observed, recorded, and reflected upon them, means something different. It means that for a brief moment, the universe became aware of itself. Not through some cosmic consciousness, but through us. Through the minds of astronomers who stayed up late, analyzing spectra. Through the curiosity of students who read about it and wondered. Through the quiet awe of anyone who looked up at the night sky and thought, somewhere out there, something from another star is passing through. This is not a small thing. In a cosmos governed by entropy, where all things tend toward disorder, where information decays and structures collapse. Awareness is an anomaly, a localized reversal, a brief, improbable pocket of order in which the universe reflects upon its own existence. Sadat so la uz. So, wei zats da. And that reflection, however temporary, is a form of preservation. We cannot stop the comet from fading. We cannot hold it in place, cannot reverse its trajectory, cannot prevent it from dissolving into the interstellar medium. But we can carry its story forward. We can encode it in language, in data, in the shared knowledge of a species that refuses to let the universe pass unnoticed. This is the fragile continuum, not a physical thread, but a conceptual one, woven from observation and interpretation, from the passing of knowledge from one generation to the next. It is fragile because it depends entirely on us. If we stop watching, if we stop recording, if we stop teaching the next generation to look up and wonder, then the continuum breaks, and the universe returns to its default state, motion without meaning. But as long as we continue, the continuum holds. And in holding, it does something extraordinary. It transforms cold data into story. It turns photons into poetry. It makes the indifferent cosmos briefly, achingly significant. This is what 3i Atlas has become. Not just an object in an archive, but a chapter in the ongoing narrative of human curiosity. A reminder that we are part of something larger. Not because we are central, but because we are attentive. And attention, in a universe that does not require it, is an act of defiance. It is a way of saying, you may be vast, you may be indifferent, but we see you. And in seeing, we make you matter. Of course, none of this is permanent. One day, the archives will fail, the servers will decay, the institutions that maintain them will crumble, and the knowledge we have so carefully preserved will dissolve back into entropy, just like the comet itself. This is not pessimism. It is simply the truth. All things end. All signals fade. Even the stars that seem eternal will one day exhaust their fuel and go dark. But here is the paradox. If meaning does not depend on permanence, then perhaps the impermanence doesn't matter. Perhaps what matters is the act of noticing, however brief, the moment of connection between a mind and the universe, the fleeting recognition that we are here, now part of the same unfolding story as the comet, the stars, the galaxies beyond counting. That moment is real, and it is enough. Because the alternative, to ignore, to look away, to live as if the universe were not worth our attention, is a kind of death, not of the body, but of the spirit, a surrender to entropy before entropy has even claimed us. And so we resist, not with anger or force, but with curiosity, with patience, with the quiet, stubborn insistence that we will keep watching, keep recording, keep asking questions. Even if the answers are temporary. Even if the stories we tell will one day be forgotten. Because while we are here, while we are awake, while we are capable of wonder, we are the universe's way of remembering itself. And that, however fragile, is not nothing. It is everything. So we hold the thread, we pass it forward. We teach the next generation to look up, to ask, to notice. And in doing so, we extend the continuum. One more observation, one more question, one more moment of awareness into the future. Not forever, but for now. And if all things fade, perhaps meaning lies not in permanence, but in noticing before the fade. In being present for the light, however briefly it burns, in saying, with all the fragile certainty we can muster, we were here, we saw, and it mattered. Chapter 25. Sleep Among the Stars. The comet is gone now. It has travelled beyond the reach of our instruments, beyond the orbit of Neptune, beyond the faint gravitational tug of the Sun. It moves in silence, as it always has, indifferent to the fact that for a brief time it was not alone. But you are still here, and the night sky is still above you. So let us rest now, together, beneath the same stars that watched 3E Atlas pass. Let us allow the questions to settle, the data to fade, the urgency of discovery to dissolve into something softer. Let us simply be, because wonder, at its best, is not loud. It is not frantic. It is a quiet thing, a slow dawning, a gentle recognition that we are part of something so much larger than ourselves that we cannot possibly hold it all in our minds at once. And that is okay. We do not need to understand everything. We do not need to name every star, catalogue every comet, trace every trajectory. Sometimes it is enough to simply know that they are there, drifting. As we are drifting, think of the comet now, wherever it is. It is not burning, it is not glowing. The sun's light no longer reaches it in any meaningful way. It is simply ice and rock, tumbling slowly through the void, carrying within it the memory of the star it once orbited. A star whose light we may never see, whose name we will never know. And yet it continues, because that is what the universe does. It continues, it moves. It carries forward the momentum of events that happened billions of years ago, long before there were minds to witness them, long before there were questions to ask. And in that motion there is a kind of peace, not the peace of stillness, but the peace of acceptance. The understanding that we are small, yes, but that smallness is not a failing. It is a gift. Because being small means we are part of something vast. Being temporary means we are part of something eternal. Being aware means we are the universe's way of marveling at itself. And so we rest now, not in ignorance, but in awe. We let the comet go. We let the data settle into archives. We let the questions linger, unanswered, because some questions are not meant to be answered, only asked. Again and again, by each generation that looks up and wonders. Imagine the galaxy now, not as a map of points and distances, but as a living thing. A slow, graceful dance of stars and dust, of comets and planets, of light and gravity. It turns gently over millions of years, and we, small, brief, fragile, are part of that turning. We do not guide it. We do not control it. We simply move with it, already part of the same vast, interconnected whole. You do not need to see it all. You do not need to understand it all. You only need to be here, now, part of it. So close your eyes, if you wish. Let the weight of the world fall away. Let the questions fade into background noise. Let the light of distant stars filter through your thoughts like water through cupped hands. Present, but not held, because the stars do not need you to hold them. They simply need you to notice, and you have noticed. You have looked up. You have wondered, and that is enough. Think now of the first chapter, the night we noticed a stranger. The moment when 3I Atlas first appeared on our instruments, anonymous and unexpected. How we did not know what it was, or where it came from, or what it would teach us. And yet we welcomed it. We turned our instruments toward it. We asked our questions. We stayed awake through cold nights and long hours, because it mattered. Because curiosity is how we honor the universe. Because paying attention is how we love it. And now, the story comes full circle. The stranger has departed. The instruments have turned to new targets. The night sky, which for a time felt alive with possibility, has returned to its usual stillness. But something has changed. Not in the sky. In us. Because we know now, more deeply than before, that we are not separate from the cosmos. We are woven into it. No use, sir. Yeah. Every atom in our bodies was forged in the heart of a star, scattered into space by some ancient supernova. And the universe, which does not speak, answers in the only way it can, through motion, through light, through the slow, patient drift of comets across the dark. So sleep now, traveler of worlds. Sleep, knowing that the comet is still out there, carrying its story into the void. Sleep, knowing that others will watch the skies long after you have gone. Sleep, knowing that the questions you have asked will echo through time, asked again by minds not yet born, who will look up at the same stars and feel the same quiet wonder. You are part of the continuum. You are part of the dance. And in being part of it, you are enough. The galaxy turns, the comet drifts. The stars, patient and eternal, continue their slow burn. And you, small, temporary, impossibly aware, are held within it all. So rest now. Rest among the stars, because both you and the comet are part of the same dream. And the dream continues, always. And so as we close this chapter beneath the quiet stars, we're reminded that every story the universe offers is both an answer and a question, guiding us deeper into wonder. If this journey has stirred your curiosity, you're welcome to stay. There are always more paths to explore, more mysteries to unfold, and more quiet hours to share together. I am the Sleeping Professor, your companion through these quiet journeys, a place where we explore the universe slowly, carefully, and always with wonder.